Hello everyone, my name is Kusal Kafle, and on behalf of all my co-authors, I'm very happy to present our work that studies the value of outer distribution testing. Current VQA datasets suffer from lots of biases. For example, for all the questions starting with what sport, tennis is overwhelmingly the most popular answer. Since the test set is sampled from the same distribution, they also demonstrate same biases, which makes it very easy to guess the answer based only on the question and therefore is not a good test of generalization. The VQA-CP dataset was introduced to solve some of these issues. It allows outer distribution testing by rearranging train and test sets. For example, for the questions starting with what sport, tennis is no longer the most common answer in the test set. Normal VQA algorithms perform very poorly on this dataset. Recently, a lot of new methods have attempted to solve this dataset. However, instead of treating VQA-CP as a test for generalization, these methods have sought to solely improve accuracy on the test set of this dataset. As a result, we may be witnessing an example of Goodhart's law in practice, which postulates when a measure becomes a target, it ceases to be a good measure. We have discovered three critical issues with existing methods that allow achieving high accuracy on the VQA-CP dataset without solving the intended underlying task. The first issue is that the existing methods rely on knowledge about how this dataset was constructed. Distributions in the dataset are created by using question prefix, and the test set follows approximately the inverse distribution as train. Methods that exploit this fact may achieve high accuracies on this dataset, but it may not generalize to other sources of bias. Second related issue is that since the VQA-CP dataset does not have a standardized validation split, many methods might be using the test set for mode of selection, either directly or indirectly. This allows finding hyperparameters that are uniquely suited for maximizing performance on VQA-CP. Finally, the value of out-of-distribution testing is only valid if it also works well for in-domain data. Ideally, the same model should work well for both in-domain and out-of-domain distribution splits. However, existing methods need to be trained separately for VQA-B2 and VQA-CP to achieve good performance. To show that the performance reporting of existing methods may be misleading, we designed several simple baselines. These baselines have no real-world usages, but they allow us to achieve near state-of-the-art performance without actually solving the task. Our first baseline randomly samples predictions following the inverse distribution of answers as the training set. This embarrassingly simple algorithm already achieves vastly improved performance on VQA-CP, especially on questions with limited answer space, such as yes-no questions, where we see over 40% improvements. In the second baseline, we train a normal VQA model but mask out its top predictions, which also effectively skews the answer predictions towards less common answers, producing large gains in out-of-distribution test set. Finally, we test a simple regularizer where we augment the data with random visual features from the same mini-batch. The goal of this model is to discourage the models from making predictions that agree with the language bias. When the regularization weight is properly tuned, this model surpasses the current state-of-the-art method on VQA-CP. Our experiments highlight a few key takeaways. Firstly, it shows that question type with limited answer space, such as yes, no, and numbers, are very easy to game. Other question types do not show this behavior, making it a much better candidate to test generalization. Finally, we find a clear trade-off between performance on outer distribution and in-domain data. By carefully selecting suitable hyperparameter, we can easily outperform state-of-the-art methods without doing anything useful. In conclusion, blindly optimizing a single metric is seldom a recipe for broadly applicable methods. In light of our findings, we have issued several common sense recommendations for methods evaluating on the dataset. First, we recommend focusing on question types that are harder to game. Avoiding yes, no, and number questions is a good start. Second recommendation is that methods should use the same model parameters to measure out-of-distribution and in-domain performance. The practice of reporting in-domain numbers after retraining should be abolished. Finally, we recommend that authors spend time analyzing true reasons behind seemingly good numbers. A good question to ask yourself is, could I design a simple baseline to test my hypothesis? We have also issued several recommendations for design a future dataset to test generalization that you can find in the paper. With that, I would like to thank you for your attention, and we hope you will participate in the question answering session to learn more about our work.